Okay, today's worksheet is going to involve more gravity problems. So I'm basically having you recap what you already know and put it all together about Newton's law of gravity and finding the value of g and things like that. So for today's lecture, I want to take some time to tie up some loose ends and give you kind of an intro to where we're headed with this, so that we're ready to go when we start the new topic on planetary motion. First thing, though, I wanted to talk a little bit about tidal forces. Last chapter, we talked about tides a little bit and how they create a torque, which is slowing down the Earth's rotation. Here's where tides ultimately come from. Now, here they show just a generic object orbiting some other object. This also applies to the object in the center, by the way. But we'll look at it here. The force of gravity that this object in the center is applying on this is right there, assuming they're all point masses. But the planet is not a point mass. So this point on the surface of the planet is a little closer to whatever it's orbiting, the sun or whatever. And so it's experiencing a greater gravitational force. Over here, it's getting a lesser gravitational force. That means as it accelerates inward, now it's not actually falling in, it's orbiting, right? It's moving in a circular path. But it still has an acceleration centripetally. As it's accelerating inward, the stuff at the surface here, on Earth it's water, but it could be rock and whatever also, is kind of left behind because it's accelerating less than the rest of the planet is. And so you get a little bulge left behind. On the surface closer to the primary body, the sun or whatever, there's a greater force, so the water or rock at the surface is pulled upward, accelerated away from the surface, and you get a bulge there. So you get two tidal bulges, one on the near side, one on the far side. The sun does this to the Earth, but of course, since the moon is orbiting the Earth, the moon does this to the Earth as well. The Earth does this to the moon. So in fact, the moon's surface does flex. The rock rises and falls as it orbits the Earth. The Earth's rock flexes too, but not nearly as much as water does. So we notice these tidal bulges of the oceans. Okay, and again, I won't go into it again here, but last chapter we saw as the Earth spins, there's a net torque caused by these tidal bulges, which is slowing us down, which has already slowed down the moon. So that's that. Now, next, they explain that. Next thing the textbook does is goes into planetary motion, and I don't like at all how they organize this, where they first talk about Newton and then they talk about Kepler. So I'm going to approach this my own way and give you a little bit of history behind the whole thing. And then we'll leave it at there. You'll do your review of gravity stuff, and then the next day's lecture, which I guess is going to be Monday, we'll talk about Kepler's laws. So I'm going to go to Paint and draw on my whiteboard here. Let's see. Oops. Now, back in the day, they thought everything orbited the Earth, obviously. The reason they had trouble with that is because the planets, you calculate where they're going to be while they're orbiting the Earth. And they found that it didn't work. The planets were in the wrong places. Some planets went into retrograde. For example, Mars moves forward across the sky. Night by night. Oops. What am I doing? There we go. Mars moves forward across the sky, but then after a while it starts moving backwards and then goes forward again. I'm going to make my marker size bigger. There. That backwards motion of Mars, and Jupiter and Saturn do it as well, is called retrograde motion. And using the Earth as the center of the solar system with the planets orbiting it, there's no way to explain that. Or is there? What they came up with is the idea of epicycles. So here's Earth in the center of the universe. Here's some planet's orbit around the Earth. So it should just go smoothly forward in its orbit, but it goes backwards sometimes. How they explained it was by saying, on that orbit, there's another circular orbit called an epicycle. So there's Mars right there. And as it moves around its epicycle, and the epicycle is orbiting the Earth, every so often it's moving backwards along its path. Now, that's kind of a lot to take in. And why would it do that? First of all, why they're using circles is because these are the laws of the heavens. And back in those days, the heavens and the earth were different things. The heavens, of course, are perfect in every way, and so everything moves in the most perfect of shapes, the circle. And so planets have to move in circular orbits, there's no question about it, according to these guys in the old days. And so the only way to make them actually do retrograde motion is put a circle within a circle, or have these so-called epicycles. And they go through the math, and it still doesn't exactly work. The planets, they do retrograde motion, but it doesn't work exactly the way we see it in the real night sky. So what they do, they put an epicycle within the epicycle. And we're starting to get really out of hand here, aren't we? At some point, we have to give up on this whole adding cycles within cycles within cycles thing. You may have heard of Occam's razor. The simplest explanation is the best, or the way he worded it, don't needlessly multiply entities. We're needlessly multiplying circles here. There's got to be an easier, simpler explanation. The simpler explanation, of course, is that the sun's in the middle of the solar system, not the Earth. Early on, you kind of get burned at the stake for saying that, so no one said it. But eventually they got away with it, and fine. We now have the sun at the center of the solar system, and planets orbiting, still in perfect circles, though. So, once again, now, I guess I should erase this. Don't bother saving it. Here's the sun at the center of the solar system. You see it glowing. There's Earth in its orbit. Here's, say, Mars in its orbit. Okay? These are perfectly circular orbits, as you can clearly tell from my drawing. Once again, you can calculate where Earth is going to be in its path, and therefore where Mars is going to appear from our point of view. As we move to here in our orbit, and Mars has moved to there, we'll see Mars at a different point of the sky. That's all fine and dandy, and with enough math, you can calculate exactly where you should see Mars in the night sky. A guy who spent like his entire career doing that was a guy named Tycho Brahe. He was the royal astronomer of Denmark. Back then they had royal astronomers and artists and whatnot. He took his entire lifetime and recorded every single day exactly where each of the visible planets were in the sky, and found that the model they were using with the sun at the center and the planets in circular orbits was pretty darn close. But the planets were a little off from where they should have been. Not as bad as they were with the Earth in the center of the solar system, but still a problem. He couldn't figure out the answer to this, and he ends up dying, and his apprentice, a guy named Kepler, Johann Kepler, gets all his data. And by playing around with all of Tycho's data, Kepler finally realizes that the planets are orbiting in elliptical paths, not perfectly circular paths. And that's going to lead us into Kepler's laws, and that's kind of, again, the groundwork I wanted to lay for where we want to go in our next lesson. Kepler's laws of planetary motion and how we understand how planets are moving around. Wouldn't be a physics class without a little story time. The kind of story about the way Tycho died was his bladder burst, and he died of infection due to that. They claim that he was, he liked to drink a lot of wine, and when you sit down with the king, remember he was the royal astronomer, you sit down with the king to dinner, you don't just get up until the king gets up. So he had to go. He drank too much wine, held it, and bladder burst. And so he died, and Kepler got all his data. More sinister explanation is some people think that instead of that, Kepler actually poisoned him to get his data. But I guess we'll never know for sure. I like the bladder burst story better. It's more fun. Anyway, that's good for today. Remember, today's work is going to be a worksheet on Newton's law of gravity and calculating g-forces and things like that. All this planetary motion stuff we talked about, this is laying the groundwork for tomorrow's lecture, where we learn about Kepler's laws of planetary motion and start analyzing them mathematically. All right, have a good day.